All right, so this week we're gonna take a look at the graphs of sine and cosine. Again, you don't need any kind of graphing calculator. In fact, I don't even think you really need a calculator for most of the stuff, if probably not anything we do this week at all. Everything we do, we're just going to do some very simple graphs, just sine and cosine. So just to kind of show you what they kind of look like. Right, here's the graph of sine. I'm going to do that one in blue, and I'll do cosine in red. So basically what you get is like a wave. Right? It's a wave that goes on forever in each direction. And sine and cosine are both waves, but let me fix it. I think I must have put the same one in twice. Yeah, I meant to put sine and cosine. All right, so here's the first one again. And then cosine, it's still a wave, but it's just a little different. It's actually what we call a phase shift. Right? Phase shift is when a graph has been moved left or right a little bit. And I'll explain exactly how much it's been moved in a little while. Right, so those are the kind of graphs we're going to look at this week. Let me show you what tangent looks like. This one's a completely different looking one. There's a pattern to it, and it does repeat over and over, but it's not a wave. Right? It's kind of like these curves that just keep repeating.
Does it connect?
No, it never connects. They're actually all separate. Yep, they're all separate. If you graph 1 over sine, remember when you flip the sign, that's the cosecant. We're not going to look at this graph either. Definitely a pattern to it. It's kind of like these U shapes and N shapes. Right? So the point I'm trying to show you is all the trig graphs that you look at, it's basically a repeating pattern over and over and over. Sometimes it's connected, like a nice wave. Sometimes it's not connected, like that. Those don't connect either. Right? We're going to look at just the ones that connect. Okay, those are the simplest two to look at. Okay, and as I said, there's 4 transformations we're going to focus on. Shifting vertically, shifting horizontally, stretching vertically, stretching horizontally. Those are the 4 things we'll do. And 3 out of 4 of those things I just mentioned, when I do them, there's an effect on the sound frequency you would hear. Okay? If you're familiar with sound or frequencies, you can look at what sound looks like using what's called an oscilloscope. That's not really listening to me talk right now. That's just a fixed sound, right? But I do have, I actually have it, where is it? Right here. So this is something that actually, it's listening to the sound that it hears over the microphone, and it makes a picture of that sound. So what you're seeing right there, that's a picture of the sound frequencies. The reason it doesn't look like a nice wave is because I'm not talking consistently. I kind of pause, I stop. Also, my pitch of my voice changes as I talk. But if I were to make like a constant sound, like if I were to whistle, you kind of see more of that wave pattern. Still fluctuating a little because I can't keep the volume like perfect. But the idea is that's what sound looks like on an oscilloscope. Okay, that's the device that turns what you hear into like a picture. So we'll study a little bit more about waves, and we'll do some different stuff with that towards the end of class. Specifically, I'm going to show you what a phase shift sounds like, right, when I do that. Okay, so these are the 2 graphs that we're going to look at. Okay, sine and cosine. And these are called periodic functions. Okay, nothing that we've studied up until this point is what you call a periodic function. So the idea of a periodic function is that the values keep repeating over and over. All right, so if I just bring, let me put the graph of sine back up. Okay, let's just take a look at it. Okay, so what you're looking at, let's just focus on like one part of it. Starting here, ending here. It starts at 0. It goes up to the highest point, which we're going to learn is 1. Comes back down to 0. Keeps going to the lowest point, which is -1. And then it finishes back at 0. So those y values, 0, 1, 0, negative 1, 0, they just keep repeating over and over. 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. You just keep getting that pattern over and over. But to see the full pattern, you have to go through this much of a distance. That distance that I just drew in black, that's how far you have to travel on the curve to see all the values before they're going to repeat themselves. So when I say that the y values repeat over a given set of x values, that's what I mean right here. This is the given set of x values. If you go any shorter than that, you won't go through a full wave of the graph. Okay? That's the minimum distance you have to go. And we're going to say what that distance is in a second. So I'm going to tell you the length of that interval right now. When you're looking at a graph of sine, cosine, tangent, any trig function, your x-axis, that's an angle, right? So like if you were making a coordinate, right, and you said, well, what's the coordinate of this point right here? Well, whatever the coordinate is, the first number that you write in the coordinate is an angle, like 90 degrees, comma, whatever it is. This happens to be 1. The y value is the highest. At that point, it's 1. So that coordinate is actually 90 degrees, comma 1. You don't have to worry about writing that coordinate right now because we're going to put it all in the table later on. So you don't have to write it. I just want you to understand that the x value, or the x-axis, is an angle. Okay, when you're making a trig graph. Now, does anybody remember how many degrees you had to go through on the unit circle to go all the way around? And once you did this, you went back to where you started. 360. So when you go from here to here, you've gone all the way through one wave of the graph, and you're back to where you started. And the length of that interval that I just traced is 360 degrees. This is 0. This is 360. Now, if you're doing it in radians, it's 0 to 2 pi. And that distance has a special name. Okay? The length that you have to go through on the graph before it repeats, it's called the period of the graph. And the graph of sine and cosine have a period of 2 pi radians, okay? Or 360 degrees. Now, that's the normal period. If you don't mess with it, you don't try to like squish it or stretch it out, you just leave it alone, like the most basic one you can have. It has a period of 2 pi radians. Right? So let's look at the graph of sine. And let me start at 0. And let me end at 2 pi on the x-axis. Okay, so what I've just done is I've set my calculator to show you exactly one wave. Okay, it is a better name, and I'll tell you what that is in a second. Now, what if I wanted the calculator's window to show 2 waves of the graph? If 2 pi would show you 1 wave, what do you think would show you 2 waves of it? 4 pi, if you double it. So if I set this to 4 pi, the calculator will change it to a decimal. Now you see 1, there's the end, there's 2, and there's the end. All right. If you set it to 3 pi, if you set it to 6 pi, you could get 3 waves. If you set it to 10 pi, you could get 5 waves. So you can graph as many as you want. We're going to focus just on graphing 1. Because if you can graph 1, all you have to do is take it, copy and paste it, and there's another wave in the graph. It's just that section repeated over and over and over. Okay? So we only have to really sketch 1. All right. So I've kind of already said this part, but what basically happens is if you graph it beyond 2 pi. You say, you know what, I'm going to keep going. You're just graphing the same thing again. It just repeats itself. Okay, so if you go beyond the end of that 2 pi, you're just copying and pasting what you already did. And you can also go before 0. Like I could take this graph and say, you know what? It goes this way too. It goes forever in each direction. Okay. But if you just go beyond that distance right there, you're just repeating what you've already done. Okay. Any question on that? Now, I keep calling that section a wave. The actual name of one of those sections is called a cycle. Okay, one full cycle of the graph. So you can call it a period, you can call it a cycle, it's pretty much the same thing. Different names are used depending sometimes on the application. I use both. But cycles is used a lot in anything with like electronics or electricity. Anybody in engineering or electrical? No? Well, if you measure the electricity, okay, in a regular household outlet, okay, that's alternating current, 120 volts. But there's something else about the electricity. It operates at what's called 60 hertz. 60 hertz. And what hertz stands for in electricity is cycles per second. Alternating current alternates 60 times per second, at least in the US, and that's how it works. So it's 120 volts and it runs at 60 hertz. If you go to other countries, a lot of European countries use 50 hertz. So if you try to plug in something that would only work on 60 in Europe, you'll probably ruin it. So like a TV that's not designed for running off European electricity, it's not going to work unless it has something built into the TV where it could work on both. Now, if you look at like your Chromebook charger or your like a cell phone charger, you know those things, they have the big black bulky like adapter thing. You know what I'm talking about? If you read that, it's like really small, but if you look at it, it probably says on the adapter something like this, 60/50 hertz, which means it's the kind of adapter that if you plug it in the US, it's going to work fine. If you plug it in Europe, it's going to work there too. So the first time I did it, I was a little nervous because I was on vacation, and if I fried my cell phone, then I had no way to talk to anybody. I plugged it in, and in Europe, and it worked fine. Like, just no problem at all. And most things do work pretty good. Just gotta make sure that's what it says on the label. All right. So when you're dealing with electrical stuff, things that are measured in hertz, they use the term cycles per second. They don't say periods per second. Never heard that before. Okay. But you'll hear me use both kind of interchangeably. All right, now if you want to make a graph of the wave of either sine or cosine, it's a little bit more complicated of a shape. Now, it's not as simple as like a straight line. We only need 2. You really need about 5 points to draw a good picture. And the 5 points are where it starts and stops. Okay, just one cycle of the graph where it starts and stops. The middle. So in this case, that kind of gives you the 3 x-intercepts, 3 places where your graph crosses the x-axis. And then you need the highest point and the lowest point. Now, that's a minimum. You can do more. If you wanted to graph 10 or 20 points, you could. But 5 is usually pretty sufficient. Now, the other thing is, notice that graph, it doesn't have any sharp turns in it. No sharp points. Everything in a sine or a cosine graph is nice and smooth. Okay, so when you sketch it, try to do your best to make it, make everything look nice and smooth. Hey, any question on that idea that you really need about 5 points to draw one of these graphs? Yeah.
What are the 5 points?
I'm going to write down what those are. I'm going to give you a table in a second.
Okay.
They're a little different for sine and cosine, because remember when we did the graph, Like for the graph in blue, when the x value is 0, the y value is 0. So basically the graph in blue goes through the origin. But for the graph in red, it doesn't. When the x value is 0 for the graph in red, the y value is 1. All right. So I'll give you both of those tables in a little bit. So every transformation that we do is going to depend on the two tables that I'm giving you right now. Without these original tables, you can't do any problem for the whole week. Okay. So everything is based off these two tables. Right? So let's start with the graph. We'll do the one for sine, and then after we'll do the one for cosine. Okay, so we're going to make an XY table. Now, if you notice, those 5 points break the graph up into 4 sections. Okay. This is the, that's the beginning. That second point is a quarter of the way through the cycle. The third point is halfway through the cycle. Your fourth point is 3/4 of the way through. And your last point is all the way through. Right? So, how long did we just say that that cycle is in degrees? From what to what? 0 to 360. What if you break 0 to 360 into quarters? 90. Each point there, if you do it in degrees, is 90 degrees apart. Bless you. All right. We're going to do it in radians. Okay, but that, if you want it in degrees, that's 0, 90, 180, 270, 360. Those are the x values. If you're doing it in radians, it's going to be 0, pi over 2, pi, 3 pi over 2, 2 pi. Those will be our x values. 0, pi over 2, pi, 3 pi over 2, 2 pi. So they're all nice and equally spaced. It's easier to see that they're equally spaced if you write them in degrees. Okay, 0, 90, 180, 270, 360. So now I just want to write the y values that go with those x values. Okay, so let's start with the first point right here. What's the y value for that first green dot? 0. Yes, it goes right through the origin. So the first y value, let's do it like this. First y value, 0. Right, second one is pi over 2. When I'm a quarter of the way through the cycle, or I'm at that second green dot, what's my height? 1. I'm at the highest. 1. And then at the next dot, where am I here? 0. The third dot, well, fourth dot, -1. And the fifth dot, back at 0. Right. So those are your y values for each one of the boxes. 0, 1, 0, -1, 0. Okay, and make sure you write down that is the table for sine. Okay, one for cosine is similar, but they're a little, the y values are a little different.
Hang on, I'm still. Yeah. Still labeling my table.
So sine and cosine are going to share the same x values. The reason we want to share those same values is because those x values are nicely spaced every 90 degrees. That's what you want when you're trying to make a graph. You want to use points that are nice and evenly spaced. That'll give you a good graph. So that's why we use the same x values. But now, let me see if I can draw the graph of cosine for you up above. And we'll see if we can get the y values. Okay, so I'm going to scroll back down because I gotta uncover the y values as we go. But cosine is going to look more like this. Let's see. Let me put the points in first. Alright, so I'm going to start up here, come down, and go up. We're going to end right there. And you can kind of see that's what it looks like on here. Alright, so for the graph of cosine, what's the first y value that you get? 1, and then 0, yep, negative 1. Yeah, so it's 1, 0, negative 1, 0, 1. And that's the table right there. 1, 0, negative 1, 0, 1. So the numbers follow the same pattern. It's just that you're starting with 1 instead of starting with 0. That's just the way cosine works. So now, whenever we do a problem, if I say like, okay, I want you to take the graph of sine and shift it up 2 units, you'd start with this original table and you would do something to it. Right? We'll talk about what you got to do. Sometimes your transformation is going to affect the x's. Sometimes it's going to affect the y's. It's never going to affect both. Okay? It could. We just in a half-year class, we don't get into ones that are that complicated. Right? So every transformation that we do this week, it's only going to affect one axis at a time. If you shift up, that's all you're going to do. You're not going to shift up and left at the same time. You're just going to shift up, or maybe you'll have a separate problem about shifting left, but they won't be together in the same problem. If we did a second week of stuff on this, bless you. Bless you. If we did a second week, we'd get into some of that, and we'd also get into the graph of like tangent and secant and some of the other ones. Okay, but we only spend 1 week on it. Okay, so this is what I just told you. So now that you got your original table, if you're going to do a transformation, you have to figure out, okay, I know what the 5 points were originally. What are they now? Like, did he tell me to shift up? So what do I do? Did he tell me to stretch it? So which value should I change? So you've got to figure out your 5. I call them the 5 key or the 5 important coordinates, whatever you want to call them. Okay, so for every transformation that we do in this class, one column stays the same. One column changes. Okay, what that again basically means we're doing one transformation at a time. So what I'll probably do on the test, I usually do about 6 of these graphs on the test. Usually I have one where you shift like up or down, one where you shift left or right, one where you stretch it left or right, and one where you stretch up or down. And then I repeat 2 of them. All right, so it's 4 transformations, you probably have about 6 problems on them. And I'll show you how to do some in a little bit. Okay. Besides graphing, there'll be a few multiple choice questions on the test. The graphs aren't really multiple choice because you got to graph it by hand. But there are some multiple choice, and tomorrow I will show you what those kind of look like. Those are pretty straightforward. But these kind of problems, the way I grade it, you can get anywhere from I think each graph is worth 12 points. So you can get anywhere from 0 to 12 points depending on what you get right. There's lots and lots of partial credit with these kind of problems. All right. So everything I've explained up until now, just been kind of like general background information about trig functions. The fact that they have a period, that's also called a cycle, and they repeat over and over. Now I'm going to talk to you specifically about one type of transformation, and that's the only one we're doing today, and it's called a phase shift. So a phase shift is just a fancy way of saying a horizontal shift. Okay, a phase shift is when you have a graph and it moves left or it moves right. And you guys have already seen an example of a phase shift. Okay, when I graph sine and cosine, they are phase shifts of each other. I'm going to show you what the equation for a phase shift looks like in a second, because that's important. When you get a problem, you have to look at it and say, okay, I see this in that spot. It means he's giving me a phase shift. Right? So you have to know what to look for. That's what I'll show you. But let's just, for a second, I want to just take a look at sine and cosine again. Okay, I'm going to make them a little bigger. So they are phase shifts of each other. You take the graph in blue, you slide it to the left a little bit, it would be right on top of the one in red. Or you could say take the one in red and slide it to the right. How much? One section. And when we graphed sine and cosine on the other screen and I was filling out that table, how much was each section worth in degrees? 90. Sine and cosine are exactly phase shifts of each other of 90 degrees. They're 90 degrees off. Yep. So what that means is if I did something like, all right, let's take the graph in red and let's push it to the right 90 degrees. All right. So the graph in red is cosine, and I want to push it right 90 degrees. And I'll explain why I'm doing this in a second. And let me go like this. All right, so there's the one in blue. I didn't change that at all. But now the one in red, I pushed right 90 degrees. And it's exactly the same as the one in blue now. Okay? But I didn't type in the same equation. One of them is sine and one of them is cosine. But they do look the same because I shifted one of them. Okay? So we're going to learn more about this part right here. That's what we're going to look at now. So a phase shift is when you add or subtract a number inside the parentheses to the sine function. Remember, this stuff right here is called the argument. X plus a number, or x minus a number. Like I just did x minus 90 on the calculator to shift it 90 degrees. Right? But that x plus some number or x minus a number, all that stuff is called the argument. It's just like if I put the square root of 3 on the board. 3 is called the argument. It's the thing you're taking the square root of. It's the number in the problem. Well, x plus c is going to be the number in the problem. It's what you're taking the sine or cosine of, either one. Right? So we just have to figure out plus is going to shift it one way, minus is going to shift it the other. Okay, we just have to figure out which way is which. Right. Let's go back to my example and see if we can figure out what happened. Okay, I'm going to put the graph back on the board, and I'm going to show you what I graphed to do it. And I want to see if you can figure out which way minus goes and which way plus is going to go. So here was the graph. And that x minus 90, okay, it's subtraction inside the parentheses. So that means it's it means it's a phase shift. Which way did that minus 90 shift it? The graph in red. Did it shift it left? Or did it shift the graph in red to the right? Right. It shifted it right. So anytime you see a minus, it's going to shift it right. What do you think would happen if I did a plus? It would shift it left. So now if I shift it left, watch what happens. I shifted the graph in red left 1 unit. Well, one kind of mark on the screen, which is really 90 degrees. Okay. Okay. So we just want to write down those two rules. So if you have x minus a value, like x minus 90, x minus 45, whatever it is, x minus a value, it's going to shift everything to the right. Now that's a little different because you might think, if you picture a number line in your head, when I think negative numbers, I think left. But this is kind of, it's the opposite. So somehow you've got to remember that if it's x minus a number, it's going to shift it right. If you have x plus a number, it's going to shift it left. Okay, so any questions on those two rules? X minus a value is going to shift it left. X plus a value, minus a value is going to shift it right. Plus a value is going to shift it left. Now, the value that you shift by right here, technically you can shift by whatever you want. Right? If you wanted to shift something left by 92.6 degrees, you could. It'll work. You could shift it left by 92.6 degrees. There are values that are more common than others when you shift. Usually if you're going to shift something, we do it by 45, 90, or 180. Those are the only shifts you're going to see in this class, only because they're the most common. You could shift by any amount that you want. All right, so now what we have to do is, all right, we know what a phase shift looks like. It's when you have sine or cosine, and then in parentheses, x plus or x minus a number. But it's got to be in parentheses. This is not a phase shift. We would look at what that is tomorrow. That's a vertical shift. That's up and down. That one's actually down 90 units. Now it's right 90 units. And if you're like, well, big deal, parentheses. It's kind of like doing something like this. The square root of x plus 3 versus the square root of x plus 3. Pretty big difference whether or not that 3 is inside the square root or outside. Pretty big difference if that 90 is inside the parentheses or outside. Totally different. So, phase shift is going to move the graph left or right. Which axis does that affect? Does that affect x-axis or y-axis? It affects the x-axis. So what that means is for a phase shift, you never have to change the y values in the original table I gave you. So when you're doing a phase shift, the first step is to copy down all the y values from the original table. And if you're not sure, what do I mean by original table? I mean these right here. For every problem we do today, if it's a sine problem, those are going to be your y values in the answer. If it's a cosine problem, those are going to be your y values in the answer. The only thing that's going to change today is the x's. So any question why the y's are staying the same? We're moving left and right. That's x-axis stuff. When we start moving up and down, then that'll be the y-axis. But that's not today. Okay, so the x's are going to change. Now, remember, it's kind of like the opposite of what you would expect. Okay? When I see minus, I usually think minus, I think negative numbers on a number line, they go to the left. But remember, if you see minus, you have to shift right. If you see plus, you have to shift left. So the first thing you have to do is look at your problem and see what has been added or subtracted. All right? So when we do example 1, I'm going to look at that and I'm going to say, all right, I got parentheses and there's a number inside it that's been subtracted. Where is it? Right here. I'm going to subtract pi over 2. So in this case, I've subtracted. Now subtraction is going to move the graph which way? It's going to move it to the right. If you think of a number line, right is the positive numbers. So what you have to do is do the opposite of that. Right? So whenever you see a minus, you're going to do a plus to each number in the original table. And we're going to go through an example. So you look at what's been added or subtracted. Okay, subtracted pi over 2. Do the opposite of that. What's the opposite of subtract pi over 2? It's add pi over 2. Where are you going to add pi over 2? To every number in the original table. Just the x's. Right, so when we do example 1, I just explained what we will do. When we get to example 2, I see a plus pi. Well, the directions say do the opposite of that. Right? What's the opposite of plus pi? Minus pi. You're going to do a minus pi to every x value. Okay? That's usually the thing that kind of trips people up. They forget to do the opposite. Because out of the 4 transformations we studied, there's 2 of them where you have to do the opposite, and there's 2 of them where you don't do the opposite. You just do exactly what you see. This is one where you do the opposite. So on your reference sheet or whatever you want to do, you're going to have 4 transformations. Next to this one, maybe you want to put a star on your reference sheet. This one is the opposite. All right. All right, so let's look at our problem. So it's sine of x minus pi over 2. Okay, now on the test, they're all going to be kind of mixed together. Right? All the transformations that we studied. Today, you don't really have to worry about which one is which because they're all phase shift problems. That's how tonight's homework will be. I think there's only like 5 problems on the homework, on the worksheet, and they're all phase shifts. Okay, first, can somebody tell me why is that a phase shift? Besides the fact it's the only one we've learned. But what about the way it's written down makes it a phase shift? Okay, what's going on in the parentheses? You're subtracting. Yep. What other operation could you do besides subtract? Addition. So the fact that it's addition or subtraction and that it's in the parentheses. That tells you it's a phase shift. Both of those things have to happen. Addition or subtraction inside the argument, in the parentheses. All right. So for a phase shift, how about, Aaron, for a phase shift, what column can we just leave the same? The y's. So when I make my table for this one, I copied the original so you can see it. I'm going to copy the y values down right now. They're not going to change. 0, 1, 0, negative 1, 0. Now if you got that on the test, that would be worth 5 points right there. Okay. This whole problem is going to be worth 12. You're going to get 5 points for each number in the y. You're going to get 5 points for each number in the x's. And then the last thing we have to do worth 2 points is make a sketch. Okay, so the table is worth most of the points. All right, now I'm going to write down all the x's, but I'm not going to put them in the table. I'm going to put them right next to it. 0, pi over 2. I'm leaving myself a little bit of room to do some arithmetic. So 0, pi over 2, pi, 3 pi over 2, 2 pi. What I'm going to grade is going to be inside that box. So now, what do I have to do to all 5 of those values? Add pi over 2. So I'm going to put plus pi over 2, plus pi over 2, plus pi over 2 to all of them. Now at this point, you wouldn't get any points for the x's yet. You haven't actually done it. You've said what you want to do. Now we have to do it. Well, the first one, that one's pretty straightforward. What's 0 plus pi over 2? It's pi over 2. Oh, just got a point for that one. Okay. Pi over 2 plus pi over 2. already has a common denominator. So when you add pi over 2 plus pi over 2, the denominator is 2. What's pi plus pi? 2 pi. Yep. So it reduces to just pi. Okay. I'm going to write it as, I'm going to leave the 2 pi over 2 over there for a second, but I am going to write the final answer as pi. I'll show you why I left that on the board in a second. Okay. The next one. Pi over 1 plus pi over 2. Okay, we have a problem with that one. What's the problem there? There's no common denominator. Okay, what would be the common denominator between 1 and 2?
2.
2. Okay, second one is good. That already has a 2. So what would you multiply the bottom by in the first fraction to make it a 2?
2.
2. If you do it in the bottom, you got to do it in the top. So now you've got 2 pi over 2 plus 1 pi over 2. What's 2 pi over 2 plus 1 pi over 2? 3 pi over 2. Yep. Okay, next one is good. It already has a common denominator. 3 pi over 2 plus 1 pi over 2. Before you reduce it, how much is that? 4 pi over 2. And if you reduce 4 pi over 2, you get 2 pi. Now again, you're going to see why I wrote it off to the side. I'm going to show you a pattern in a minute. And the last one. Well, 2 pi didn't have a denominator, so I just put 1, just like I did with pi. What's my common denominator in this last one?
2.
2. So what would you multiply top and bottom by?
2.
2 and 2. So now you've got 4 pi over 2 plus 1 pi over 2. 5 pi over 2. And if that's what you wrote for this problem, you'd have 10 out of 12 points right now.
Can you simplify this over 2, or do you want to just leave it like
No, we're just going to leave it just like that. You don't have to write 2.5 or 1.5. No, we just leave it just like that. Now, watch this, right? 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. If you don't reduce them, you'll always see a pattern. Okay? In this case, it's just going up by ones. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So if I wanted to graph the next cycle, it would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. And if I want to do another one, 10 pi over 2, 11 pi over 2, 12 pi over 2, 13 pi over 2. I just keep going like that. Those would be the x's, and these would be the y's. 0, 1, 0, negative 1, 0. 1, 0, negative 1, 0. 1, 0, negative 1, 0. Just going to keep repeating that 1, 0, negative 1, 0. These are the same. Remember, when you look at the graph of sine, it always ends exactly at the same height that it started. 0 and 0. Right. So now the last part. Let's make a sketch. Now these x values are kind of messy numbers. Like pi over 2 is like 1.57. Pi is 3.14. So you don't want to label your x-axis like 0, 1, 2, 3, 4, 5, 6. You can label your axis any way that you want, as long as you're consistent, right? Each gap has to be worth the same amount. So you could go like 2, 4, 6, 8, 10. Okay? What I'm going to do is I'm going to label it with the values in this column, because every value there is equally spaced. If you looked at them in degrees, the top one is 90, 180, 270, 360, 450. They're all 90 apart. Right? We're just not going to write them in degrees. I think it's easier to see in degrees that they're equally spaced. Okay? But those are. Another way you can tell they're equally spaced, you had a nice pattern when you went through them. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Those are all nicely spaced numbers. Right, so let's put those labels right here. So that's 0. You don't have to put 0. I know the axis is 0. But if you want to put it, you can. Pi over 2, pi, 3 pi pi over 2, 2 pi, 5 pi over 2. The reason I didn't put my labels up higher is because I'm going to be drawing a picture in here. If I put my labels up higher, I would have had to draw through the labels. It's not a big deal if you do that, but that's why I usually put them a little lower. Now, this is 1, and that's negative 1. Okay. And now let me scroll up so I can get my points. Pi over 2, 0. That's the first one. Next one, pi 1. Okay. Third one, 3 pi over 2, 0. 2 pi, negative 1. Now on the homework, it's already graphed. There's like graph paper photocopied onto the homework, so you're not going to have to worry about trying to sketch it by hand, because sometimes it's hard to kind of line things up. And then the last one, 5 pi over 2, back to 0. Okay, and draw your sketch. And just try to make it look curved. You know, mine doesn't look, it doesn't look like it's straight. It kind of looks like there's a little bit of a curve to it at least. And that's it. That's your graph. So the table would be 10 points, and then the graph would be 2. Now, on the homework, what I'm going to have you do is graph the original, which looks the same every single time. So the one, I'll just do it in black. The one in black is the original. Okay. I'll probably have you do it on like separate axes so it doesn't look confusing on the same, but I'm just trying to show you the one in red, it moved to the right. Okay. How much? It moved exactly pi over 2 units to the right. And that's pretty much what every graphing problem is similar to this week. Any questions on that? Okay, so that was a sine, and we shifted to the right. Let's try a cosine, and this time we're going to shift the other way. Okay, so first thing you always want to do, look at the problem and figure out which of the 4 transformations you're dealing with. Can somebody tell me which transformation this one is? And then my next question is going to be why. You have a guess, Peter? You have a guess what kind of transformation this one is? Give you a hint, we've only studied one so far, so you don't have too many options to pick from. What was the last one we did? What did we call it? It was a 2 words, blank, blank. Sure. What's the title of the section? Title, yeah. Title of the section.
Graphs.
Yes, I think I had one other thing in the title, I hope. Yes?
Phase shift.
Phase shift, right? Graphs of sine and cosine. Phase shift. So we're doing just the phase shift. So that transformation is a phase shift. All right, now I have another question. Why? Why is that a phase shift? It has addition. What else could it have? And where is it? Because that's important. Where is the addition, or this could have been subtraction? It's in the parentheses. You take those parentheses out, that's a problem we would do tomorrow. That's not a phase shift anymore. Okay? So that's a phase shift. It has addition, it's inside parentheses. Okay, so let's figure out which column stays the same and write those values down first. So Aiden, when I write my make my table, which column here is going to stay the same?
Your X. Or no, Y.
Y.
Oh, you asked ask why?
Yeah, I asked why.
Oh,
But yeah, why do y stay the same? A little confusing.
Is it X is in the parentheses or no?
Well, what kind of transformation is that?
What's it?
Peter, what kind of transformation is this? What kind of transformation is this?
Phase.
It's a phase shift. So tell me more about a phase shift. Yeah. Oh, phase shift moves things left and right. So if you think of your axes, when you move stuff left and right, that has no effect on things moving up and down. Right? When you move left and right, all that affects is the x values. Right? Imagine you had a point here, and you gave me the coordinate, and I said move it to there. Well, if you move it right, it still has the same y value. All you did was change the x. Okay? So moving left to right doesn't affect the y values at all. That's why they stay the same. All right, so now, what are my y values?
1, 0, -1, 0, 1.
Yes, and a lot of people, sometimes they look at the wrong column. They look at the sine column and give you those. If you did that, you'd get all the y's wrong. You might still get the x's right, but then your y's would be wrong. So you'd lose a lot of points for that. All right, so your y's, 1, 0, -1, 0, 1. Exactly what was that, Libby? Did you say it? Okay, exactly what Libby said. Now, for cosine, when you're doing a phase shift, yes.
What about sine?
No, sine has a different table.
Sine is 0,
Sine starts at 0. Yep.
Chase specifics.
All right, so now what I always do on the outside is put the original values, leave a little room to do some arithmetic, and then inside this box, I'm going to put my final answers. So now I need my original x values for cosine, but don't put them in the box. What are my original x values for cosine? And they're also the same for sine. Yep.
0, pi over 2, pi, 3 pi over 2, and 2 over pi, I think. 2
pi,
yeah, 2
yes.
pi, that.
Now, are we going to add something to those, or are we going to subtract something?
Subtract.
Yes, we're going to subtract. And how much are we going to subtract? Pi. We're going to subtract pi. Well, if you think of it in degrees, you're subtracting 180 degrees. Pi, 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 pi. All right, so I'm going to do the first, the third, and the fifth one, because those are the fastest. 0 minus pi is negative pi. Pi minus pi is 0. 2 pi, take away 1 pi, is 1 pi. I can do all those because they already had common denominators. Now, the other ones don't. So, I had pi over 2 minus, I'm going to make it pi over 1. Kind of like the last one. What's the common denominator here? 2. Double the bottom, double the top. So you have 1 pi over 2, take away 2 pi over 2. What's that going to be?
Negative pi over 2.
Yes. So you have 1 pi over 2, take away 2. 1 take away 2, that gives you a negative 1 pi over 2. Now the next one, let's look at what happens there. That's going to be what you had just said. 3 pi over 2, take away pi over 1. Common denominator again is 2. 3 pi over 2, take away 2 pi over 2. 3 take away 2 is 1 pi, and the denominator is a 2. Questions on those x values? Yep.
We're subtracting because the parentheses says plus.
You always, when you do a phase shift, yep, you always do the opposite of what you see in parentheses.
Okay.
I'm not saying you do the opposite for everything we're going to learn tomorrow. But for today, you're going to do the opposite. Yep. Now, if you look at that, it doesn't really look like there's a pattern there. Okay? But there is. If you didn't reduce it, you'd have negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. I can keep going. All right, so there is a pattern if you write everything with a denominator of 2. So 5 points for the x's, 5 points for the y's. Last step, make your table. All right, so now I need 2 marks into the negative x-axis. Right? If you want to think of them in degrees, that's negative 180, negative 90, 0, 90, 180. They're all 90 apart. Just make sure you start here. Negative pi over 2. 0, again, I'll just put that right on the axis. And you know what? I should probably move these numbers a little lower. Again, if you don't, not a huge deal, but you're going to end up drawing over your numbers. So 0, pi over 2, and pi. Okay. So what I usually do is I just look at the y's and I say, okay, 1, 0, negative 1, 0, 1. That's a pattern that comes up a lot. So by the end of the week, you'll probably know that. 1, 0, negative 1, 0, back to 1. So I just graph those 5 points right there. Now remember, this is a wave. What you're graphing is like the middle part of it. Okay, that's just the way it worked out. So in cosine, we just end up graphing like the middle section. It looks kind of like a V, but just try to make it look curved. Don't draw it like that. It's not like a V shape. It's a little more curved. All right. So sometimes what I do is I just kind of like pretend like I'm drawing it like that, and then it would continue on. You don't have to draw the dotted part. I just use that to try to get the curve of how it should look. Okay. And there's your sketch. Any question on that? Okay, so we'll do one more of those, and then that'll be the last one. Okay, so back to the sine function. This time we're shifting by pi over 4. So the first shift I gave you guys, that was a shift of 90. This was a shift of 180. That's a shift of 45, if you were thinking of it in degrees. Pi over 4 radians is 45 degrees. Now, I want to get to the point where we have to do the graph, because that part's a little tricky, just with setting up the labels on the axis. The table is pretty much the same. Right, so Caitlin, which column is going to stay the same? The y's, because this is a period change, this is a phase shift, and we talked about why it's a phase shift. So what are my y values for sine? Yeah?
0, 1, 0, negative 1, 0.
Yeah, very good. And what are my original x values for sine? Yeah, Jake?
0, pi over 2, pi, 3 pi over 2, and 2 pi.
Yes. All right, so we got those. And now, am I going to add or subtract?
Add.
Add. And someone else tell me how much. We're going to add pi over 4. Now, this is one where I'm probably going to do the first one or maybe the first 2 or 3, but then I want to look for the pattern because none of these have common denominators. But once I see the pattern, I can just fill it in. Okay? So let's start with the first one. What's 0 plus pi over 4? Yeah, so that one's easy. Now the next one. Pi over 2 plus pi over 4. You know what, actually I could probably squeeze it in here. If you have room, you could do it right there. I don't quite have enough room. So I'm just going to do it over here. What's the common denominator between 2 and 4? 4. Double the top, double the bottom. So now you got 2 pi over 4 plus 1 pi over 4, which is how much? 3 pi over 4. Now, based on the pattern you see there, 1 pi over 4, 3 pi over 4. Anyone think they know the next one? 5 pi over 4. And the next one? 7 pi over 4. And the last one? 9. If you find denominators of 4 each time, that's what will happen. Now, even though the graph is a little tricky to set up, if the problem's worth 12 points, you just got 10. So the graph is only worth 2, and it's still worth something, but the table is definitely way more important. So is there any questions on how we got those x values? Okay. So now, let's take a look at, let's pretend we had to put these numbers on a number line. You wanted to label, and you had a number line like this. And 0 was right there. Now, could I do this? -3, -1, 0, 1, 3, 5. Is that okay?
Yeah. No.
What's wrong? I skipped, like, what am I going by? Okay, from 0 to 1, you're saying that's 1. But then you go 1 to 3, now you're saying it's 2. Well, which one is it? Is the gap between them 1 unit each or 2 units each? That's the mistake that some people make in this problem when they label it. That's like a simplified version of it, but I think that's easier to understand because it doesn't have pi in it yet. All right? So you just have to make sure your spacing is consistent. All right? So let's see if we can set it up here. Let's start with pi over 4. Now, if you wanted to think of pi over 4, right, that's 45 degrees. Triple pi over 4. What do you get if you take pi over 4 and triple it in degrees?
Like 125.
How much?
35.
135. So this one is 45, 135, that's going to be 45 times 5, which is 225. The next one is 45 times 7, which is 315. So I'm just putting it in degrees so you can kind of think what's happening here. How much do you add to get from 45 to 135?
45. No.
90.
90. How about what do you add to get from 135 to 225? 90. 225 to 315? 90. So you're adding 90 from here to here, from here to here, from here to here. That last one is, let's see, that'd be 405 if you wanted to write it, but we don't need it. Right? So you're adding 90 each time. But look at the first one, 45. Well, you know this is 0. You know that's 45. So how much is this space worth? That space right there is worth 45. Okay? That's the way we labeled it. Each one of these numbers is 90 away from the next. 135, 225, 315. So where do you think you would put 3 pi over 4? Keeping in mind that it's 90 away from pi over 4. Yeah, it would go right here. Right? This is 45. This is another 45. This is another 45. 3 pi over 4 is 90 away from pi over 4. That's why you have to put it there. The only time that this weird kind of thing ever happens is when you're dealing with the 45s. Okay? And the real reason is because you don't have 0 in the table. It's like we kind of skipped over it. All right? So that's the only time you need to check for it. And what I do is I usually put it in degrees, and then it helps me make more sense of it. All right? So the first one's at 45, and the next one is 90 away. And now it's going to be consistent from here. The next one is 90 away. Next one is 90 away. Do I need one more? Yeah. 9 pi over 4. Okay, so 45, and then there's the next one, next one, next one, and that's why I labeled them the way I did. Okay. Question on that? That's the only tricky part with that one.
Wait, I actually have a question.
Yes.
Within the parentheses, does it say it's like a cosine?
If it's outside the parentheses,
No, but it's in the parentheses.
if it's in it, yep.
It's always going to be the opposite of what?
Yes. Yep.
Okay.
Phase shift is always the opposite.
Okay.
And now setting up the axis was the hardest part. From here, it's pretty easy. So pi over 4, we're at 0. 3 pi over 4, we're at 1. 5 pi, you're back at 0. 7 pi over 4, see this is where I should have put my labels lower. Oh well. So I'm at negative 1 and back to 0. You'll know if you don't sketch something right, you'll kind of know, because if you didn't space your points out the way I just did, you might get something that looks like that. It's like part of it looks kind of squished and the other part is stretched out. That probably means you just spaced something wrong. Right? But these look nicely spaced, so that's good. Then probably should move those labels down. So that's phase shift. Any questions on that? Okay. So the homework tonight will be a worksheet. I think there's five questions on it. Each problem is set up like this. It's got a spot for the original. The original is the same every time. If you do sine, it always looks the same, or if you do cosine, it just matters which one you're doing. And then there's a spot for the final. So show me what the original looked like, and then show me what it looks like after you shifted it left or right. Okay? It's what we just did on this one, but it's two separate graphs. You don't have to do them on the same graph. Okay? And make sure you show the table. Okay, that's how it is on the test. There's a blank table like that for every problem, and you just have to fill in the table. Okay? I'm not sure if I put that table on the homework, but it's definitely on the test.
Oh my god.
Yo.